Okay, so we're discussing free processes now, of course, and today's topic will be Compton scattering and its inverse. You know. No. Compton scattering, inverse Compton scattering. Yeah? We will see what I mean by that. It's a little bit upside down here, contemporary thing. Anyways, we have actually already sort of encountered a certain limit of this, because you can say that Compton scattering is more or less the general case of our previously considered Thomson scattering, right? Or vice versa, Thomson scattering is actually the low energy limit of the general case, which is Compton scattering. So now we know what it's about. It's about free electron scattering, free processes, where we are. Where we have this general picture, right? We have some incoming photon with some energy, h nu, which is scattered off this electron here, which is free, in some direction with some then out after the collision. I'm going to call it today h nu out. Okay? So we can now, for the purpose here, we can put this in some plane here, call it x. So we have y and xy plane here, right? So what we did before was essentially that, okay, we assumed that this collision was what we call elastic, such that the incoming frequency was equal to the outgoing frequency. There was no shift here. That means that there were no kick on the electron, you know. We didn't account for the fact that, as I have mentioned in other classes, well, if you look at this now from a particle perspective, think about your collision in your physics course, right? Then the photon comes in here, and I'm the electron now, and it kicks me a little bit, so I'm going to jump back, and then it might scatter off. And of course, that kick is going to be just like in your standard collision, right? If it's just grazing me like this and it's continuing that, I'm not going to feel anything. But if it's complete backscattering, dunk, dunk, yeah, then it's going to be the most effect felt. The thing is that the electron, or me in general, we have a lot of inertia, right? So here in the room, because of the lamps, the reflected lights, etc., there are some photons hitting me constantly, yeah? But I don't really feel like I have to fight against them, right? Because, you know, I have a lot of inertia. So we don't feel this in our daily life. Now, similarly here, in this case, what we actually considered was the cases where the electron's rest mass is much, much bigger than the incoming photon frequency, okay? Such that the electron's rest mass, which is then MEC squared, is much larger than this, nu molar, then it remains as rest, also after the collision, approximately. And then nu equals to nu out, and that was our Thomson limit, right? But, of course, if we have now very high energetic photons coming in, this might not be valid. And then we have to set up, just like in a standard collision, the conservations of energy and momentum for this system in order to calculate. And one can think, okay, will this ever be important? Well, it turns out it's actually in the early universe, for example, critically important. because it's the Componisation, which is a concept we'll come to, that keeps the early universe, the photons and the baryons, the electrons in this case, and the rest of the baryons, well, the electrons aren't there, but it's the Compton scattering process that actually keep them locked to each other, that they have the same temperatures, that is, that they're in thermal equilibrium, which is something that we already, so to say, assumed when we did all our calculations for the era of recombination, right? We assumed that they were together, we could use the equation, etc. They were locked in, and they were freely streaming after when we did all the calculations. But you could have asked yourself, well, if we assume that it's Thomson scattering, how can they be locked into each other? Because that's a complete elastic scattering process, so that there is no energy exchanged between the gas and the radiation, right? And then they could just be decoupled, even if there is a lot of electron scattering going on. But there is a small thing that turned out to actually be enough to thermalize the early universe. Now, we will also see that the inverse process here can be very important, and that's actually the inverse Compton scattering is, as we will see toward the end, critically important for taking low frequency photons now. So that's inverse, low frequency, but with high energy electrons interactions. So you can think about, again, your cosmic background radiation photons, but now not in the early universe, but as they're flowing toward us, they're very low energy now, 3 Kelvin today, you know. But then when they fly through a hot plasma on their way to us, they can actually be subject to the inverse Compton effect. And this is called the Sunayev-Zeldovich effect, where you see background radiation photons subject to the inverse Comptons when they go through the hot intra-cluster gas that exists, well, intragalactic gas that exists between the individual galaxies and galaxy clusters, okay? And this actually is a critically important effect for mapping out the large-scale structure in the universe and seeing how that agrees with various models for structure formation. All right, so that was, so to say, the setup. Now let's do this. Well, then we have to, so to say, set up the system. So we're going to consider the energy conservation. Before collision, we have h nu, plus we're going to assume that this is at rest in the beginning. So the electron now is at rest at the beginning. So it just has its rest mass energy. After, well, we have the photon energy h nu out. But now we're going to assume that the electron can have some kinetic energy as well. And it has then gotten a little push with some other angle, which we will call phi, and we will call the photon angle theta. I'm going to put it in that direction. Now, this energy then is just then, as we know, it's me squared c4 plus p squared c squared. So that's just the total energy, including some momentum of the electron afterwards. This is just a special relativity formula for you. All right. Momentum. Well, we put it in the plane. So we have in the px plane now, well, the photon is coming in that direction, so then the incoming momentum is just h nu over c. This we know by now. The electron had no incoming momentum, right? The outgoing momentum then is going to be h nu out divided by c, and then, well, in the x direction here, we put it a scattering angle to theta, so it's just going to be cosine of theta then, right? Now, the electron, though, also has some momentum in the x direction, which will be then p, that's the magnitude, and then it will be cosine of the phi angle here, which is that scattering angle. All right. And then we have the py plane here. Well, the incoming photon didn't have anything in the y plane. We put the collision in the x plane, right? We're free to do that. That's just 0 plus 0. The outward then will be h nu out c sine theta, and then I have to put the minus because I put the phi angle in this direction, right? So p sine phi there. All right. Well, there you go. 3 equations, 3 unknowns. Our task is to show that nu out is nu in, or nu as I called it, 1 plus x, 1 minus cosine of theta, where x is h nu divided by mcc squared. Okay. So we can just do this. Simple task. Well, people have been doing this, right? So we know that this should work out. But I thought we will actually do it, okay? Because there is sort of a classical physics type of problem, which again, I think is good to do in the context of this. It also gives us some training in how, when we do this type of exercises, how we can think, right? So, well, the first thing is we want to show this, okay? This is what people have found, so this is what we know should come out. It doesn't involve the phi angles, right? So it doesn't involve the scattering angles of the electrons. So that's our first clue here, what we need to do in order to get to this from these conservation laws. We need to get rid of those. Well, they involve the cos and sine, so it's probably a good thing to square them then, right? So we're going to square this and we're going to square this. Okay? So in the px then, we have p squared, cosine squared. And then we don't want anything more, because that's what we're going to get rid of. So we're going to put that out on the other side. So that's going to be then h divided by c nu minus nu out, nu minus nu out cosine of theta, right? That's just me putting them on the other side there. And we're going to square it. Then we're going to do the same thing with pi. So that's just p squared sine squared phi. Nice, right? Is equal to, and then we had just this term, right? So it's just h nu out divided by c sine theta squared. Here you have to help me because, you know, I always mess up the algebra when I do this, believe me. So when you see an error, then it's like, yeah. Okay, so the point is that we add this, of course, and then we get rid of that. So we have p squared equals 2. We have added them, right? So it's going to be h nu. And then we see that we have c's everywhere here, right? So we have a c and we have a c. So we're going to put c squared up on that side. So that's h squared now. Nu minus nu out cosine of theta squared. Then we have this one. H nu out. We can just square them. Sine squared theta. All right. So that's what we have. Let's frame this. Call it our number 1. Yeah. So the second thing that we should realize now, okay, we use the momentum, so then it's likely a good idea to use the energy now equation, right? We have a square root there. That's also not very pleasant, huh? So we're going to square that too, so we get rid of it. So we're going to take that one, square it, and then we get from the energy conservation me squared c4 plus p squared c squared. And that's nice because now you see that they correspond, right? And that's going to be then equal, and then we have all of these on that side. So it's going to be h nu minus nu out, right? And plus MEC squared, and I'm going to have to square it. All right. Actually, let's write this down because we can realize that this guy seems to be over there. So we can write this out. Huh? That's going to be h squared, nu minus nu out squared, plus 2h nu minus nu out, MEC squared, and then we're going to square the last one, which was the goal, C4, because then we see that these cancel immediately, and didn't I? Yeah, you can check this. And what they do, oh my God, it was so much water. Messy. All right, so now we have some new equations, right? So now we can take this away. Can work with those, and we see where we go. Do we remember this picture as well? Yeah, we do. Otherwise, we draw it again. Okay? No, my upside down was vanished. You don't want to be stuck in the upside down, so to speak. What was I doing? Right. We had the second equation here from the energy, and then you see that and that. We can just equate them, huh? So, okay. Let's write that out. H squared, yeah? Nu minus nu out cosine of theta squared plus, it should be a square there, there is a square there, h squared nu out sine squared theta. Okay, yeah, that's as it is. H squared nu minus nu out squared plus 2h nu minus nu out MEC squared, and that was it, I think. Yes? I feel like I've missed something. Okay, perhaps I haven't. So, well, there's sort of no squared, cosine or square there, so we have to try to get rid of those as well, right? But we have a sort of clue here that we can get rid of them, right? So let's see if we can work with the left-hand side here a little bit better. Writing this then as h squared, nu squared, right? And then I have a minus 2h squared, nu out, okay, this looks better, cosine theta, plus h squared, nu out squared, cosine squared theta, and then we have plus h squared, nu out squared, sine, yeah. So you can see that these, of course, adds up in the same way. So we're in a good way. This we have to keep, yeah. And that's equal to this here, which let's write that out as well then. Nu squared, and then we have a minus again, so 2 nu out plus h squared nu out squared, right? It's just me writing out the steps. MEC squared. Neat. So, do we have some cancellations? Hopefully we should have seen this, yeah? This. There's a bunch of 2's here. this, this, this. Okay, wow. Put that one over there, take that one minus, yeah? Nu out, 1. Right. Did I do an algebraic mistake here somewhere? Like I said, I typically always do that. And now I've gotten a bit lost. Were there some age somewhere that were not supposed to be there? Or how did we go about this? Let's just write it out, okay? Let's do another step. What did I cancel? I canceled the 2's, right? So essentially I have the h squared still there. Nu out equals 2 minus, yes, I forgot the h squared there. Yes, there was the issue. Minus h squared nu out plus h nu minus nu out mec squared. So my point was we had some sort of x there, so we want to divide, if we can, by nu h, right? So if we divide this now by nu h by nu h by nu h or h nu, can see that it cancels there, and then we have another h that we need to get down, because otherwise we don't get it there, right? And we can move that over, so we see that it's nu out, and there is a cosine of theta somewhere floating around here. From there, the 1 minus cosine of theta equals, these cancels, we have an x there, so it should be nu minus nu out divided by x. Whew. And there's no nu there, of course. Those canceled. Yeah? Okay. This looks good, because what we can do now, of course, is to just put up the x and then take it over. So we have nu out 1 plus 1 minus cosine of theta x equals to nu. And if I'm not mistaken, is that not what we were supposed to show? Indeed. All right. So that actually worked out. Like I said, it's a bit of an algebraic mess, but I do like the exercises in the sense that it also gets you thinking in, you know, how you often solve exercises in various physics courses, you know. You have to think what you need to square. It's energy, it's momentum conservation. What do we need to get rid of? What do we want to get rid of? Yeah, etc. So now we have the frequency, right? Now we can start to think about what this means. Well, first, of course, we want to make sure that we preserve the old limit that we had of Thomson's gathering. Thomson's gathering, we know, we said that, was the low energy case. That is, the electron has a lot of inertia as compared to the incoming photon. That means that h nu is much, much smaller than mec squared, or put in this case, x is much, much smaller than 1, goes to 0. So, indeed, when x goes to 0 here, this is not a difficult equation. When x goes to 0, nu out goes to nu. That is, that we recover the Thomson. Okay? We can also see that it makes sense how we define the scattering angle, right? Because if we have collision that's not happening, just the grazing, right, like this, then cosine of theta will just be 1. If cosine of theta is 1, this is again 0, such that nu out equals to nu. Nothing happens, as it should. And we also see that we get the biggest effect for backscattering. Backscattering here, cosine of theta is -1. We get a 2 there. That's the maximum effect that we can get, which is also what makes physical sense. You come in, head on, that's the maximum collision that you can get. Right? Forward scattering doesn't change it at all. Backscattering, maximum effect. The angles in between, effect in between. All right. So there is another interesting thing we can do here, and if we write this now in this way again, that it's nu out plus nu out x1 cosine of theta equals to nu, right? And then if we subtract now the nu out on that side and divide it by nu, we get to nu minus nu out nu minus nu out, we divide it by nu out, okay? That's just now x1 minus cosine of theta, right? And then we divide this again by nu, and then you see what happens with your x there. This is just h divided by mec squared, 1 minus cosine of theta, the point of this being a constant. But then you can look at this left-hand side and you can realize, all right, but we have our standard relation, lambda c divided by nu, so this one here is just if you just multiply this now by c, we see that this is going to be lambda out minus lambda, which is then our delta lambda. It's just going to be h divided by mec 1 minus cosine of theta. So if you put this now in wavelength space, you have a constant shift, which is then independent of your incoming. That's not the case for the frequency, right? Because the shift involves the frequency itself. But if you look in the wavelength space instead, and then you just consider the delta lambda here, then you see that this is always a constant. And this constant here is indeed called the Compton wavelength, which is why I wrote it as lambda c, and it has a very small numerical value of h MEC 0.04 angstroms. So this is to show you that in each of these Compton gatherings, the wavelength gets increased by 0.04 angstrom. So a tiny effect indeed, which must be because we have to preserve the elastic limit, right? Now, this also then comes with a corresponding shift in the cross-section, and that I'm just gonna give you an approximate formula for this. It's the Thomson 1 minus 2x, okay? Where x is the same factor as this one, right? So to derive this is called the Klein-Nishina formula. You would have to go into quite deep into the quantum mechanical picture of this, which is beyond the topic here. But what you can see is that, again, this shift as compared to the Thomson cross-section is going to be very small as long as we have small x, okay? And indeed, I can tell you that for all practical research applications that we do, we use it as a constant. We do not have to care about this shift because it's so small, okay? That being said, there are instances where you would have to do this. One thing that I mentioned is that, for example, a couple of years back, I had some discussions with a researcher trying to calculate the radiation force and perhaps have these type of radiation-powered wind outflows that you know that we work on in my group, but not from stars, but from the surroundings around the neutron star. And the neutron star is, you know, kind of dense, and it's kind of hot down there. And there, one would actually have to take into account of these effects. That is, taking into account the Klein-Nishina formula and the deviation from the Thomson cross-section. And that could actually then lead to an increasing as you move away and the material starts to cool away from the neutron star. In this case, it could lead to an increase in cross-section as a function there because of this effect. And that could be important there as just one example where one would have to take this into account. Like I said, for our daily research, the Thomson cross-section as it has always been sufficient. Now, another way to show that this is a really small effect is, of course, okay, but imagine now we have a black body radiator, okay? And we want at the peak of that black body radiator, we want the effect to be x 10%. We want a 10% effect in the change here. What temperature does that black body have to have then? If we want this to be at the peak, right? Well, we know all of this already. We can just set up Wien's displacement law, we've done many times. Look up knowledge in our notes, what the numerical factor here is, centimeter Kelvin, okay? And we have x that we want to be that. That's, of course, hc lambda max now. We want it to be at the peak. MEC squared, okay? And then, well, we have this. We need it to be 0.1. We have all the others. We can just solve for t directly. I did this, and you check my algebra on this by doing it afterwards yourself. It came out at around 10 to the 8 Kelvin. So this is my way of showing you that in order to get this effect to be significant, even 10%, at the peak of a black body distribution, you would have to have a plasma that is 100 million degrees, which, you know, is very hot indeed. That being said, we know that from other discussions in the course that it can be significant, if not at the peak, then in the tail. Remember that there is always, at least if you're in a thermal situation, there is always a high energy tail, right, of photons, which have much higher energies than the flux peak. And we use this to discuss various other effects that we have seen in the course. For example, why ionization, recombination, happens at lower temperatures than one would expect. And this was again then in our course in view of the recombination era, right? In that context. So this then can be important. Also, we have that. So we can also now, where did we have our delta lambda here? We can take our delta lambda now, which is just this constant, and then if we want the relative, we're going to have to divide it by lambda. Okay, so how much is the shift as compared to the initial lambda? And then we see that this is just age divided by MEC lambda, right? 1 minus cosine of theta. But if we now multiply this with a C there and a C there, we see that H, that's just the photon energy. So we can call this the energy of the photon, right? Hc divided by lambda, divided by the rest energy of the electron. And then we have 1 minus cosine of theta. And then we say that for this process, remember we talked a little bit about that there was a phase angle for the Thomson cross-section, so that it's not completely isotropic. It was this 1 minus cosine factor. However, it is still what we say fore-aft symmetric. That is, that's, if you consider now many scatterings, many processes here, as many will be scattered in the forward direction as there are in the backward direction. So on average, when this has happened many times, the angle average cosine of theta will be 0. So if you take an average delta lambda over lambda, that will be gamma of there divided by mc squared, which we can call epsilon. And this epsilon now is the Componisation factor, which happens after many processes. And what you can see is that delta lambda increases. Now, what happens? Well, delta lambda increases. That means that the photon energy of the photon, is decreasing. So there is a degradation of photon energy, and of course that has to be delivered somewhere. And in this case, it's delivered, as we saw in our initial picture, to the kinetic energy of the electrons. That was our initial case. Now, kinetic energy of the electrons, that is just how we have assuming some distribution. In our case, a Maxwell-Boltzmann always distribution. That's just related to the temperature, right? So there is a degradation of photon energy. It delivers kinetic energy to the electrons or kinetic energy to the gas, so it heats the gas. T gas goes up. This effect then is called Comptonization. It's how you can, with very high energy photons, deliver some of that energy into your gas and thereby heating it up. Like I said, a very important effect for establishing equilibrium between the photons and the protons and electrons in the early universe. All right, that was our Comptonization. Now, the second part of the story. So, if we go back to our picture, nu, electron, H nu out, plane theta, plane phi. We call this the inverse. And why is that? Well, now we are going to consider the case where we have low incoming photon energies. So this one is low, right? But the initial electron is not at rest. It's actually moving very, very fast. It's moving relativistically fast. That is, we have a very hot gas that is with a high T, that is interacting with low energy photons. And that was my discussion, of course, in the beginning relating to that. So then we have to keep our we have to differentiate between what we normally call the co-moving frame of the electron, in this case. I mean the frame where the electron is at rest, which often is called also the particle rest frame in relativity, and what we often call the observer's frame in our context, which in relativity often is called the laboratory rest frame. Okay? Now, in that, we can then set up our normal Doppler shifts formula. So nu CMF again is just nu 1 minus cosine minus V over C cosine of theta, and the inverse nu equals nu CMF 1 plus VC cosine of theta in the co-moving frame now. Now, of course, since this I already mentioned that this is the relativistic limit, otherwise we don't get much here. We have to add our lovely gamma factor. We have to multiply this by the gamma factor so that we get the relativistic Doppler effect, where the gamma factor is our 1 over square root of 1 minus V squared C squared. Okay? And then we can just set out this that nu out after the scattering will just be nu co-moving frame out, okay, gamma 1 plus V over C cosine theta co-moving frame, like that, like so. And then we need to do the realization here, and that is that, okay, but what did we say this was? We said it was a low energy photon interacting with a high energy gas, right? So that's why we could get relativistic effects. But of course, this is a matter of frame, because if we now translate ourselves into the atom's frame, the frame of the electron, then in that frame, the electron is not moving. We're standing still. And if we're standing still, yeah, we just have our rest mass, well, but we have a low energy photon interacting with us, well, then we're in the Thomson limit. So in the co-moving frame, nu co-moving frame of the atom equals to nu out co-moving frame, because in this, per definition, we're in the Thomson limit. Okay, so, well, that's nice, because then we can just swap this to nu CMF 1 plus V over C cosine theta in the co-moving frame here. And then we can use this again to get nu gamma squared 1 plus V divided by C cosine of theta CMF 1 minus V over C cosine of theta. And we can actually see here that from this we can get an angle shift. We can actually get things like beaming in this, which are interesting relativistic effects here, but which is not something that we actually talk about in this course. That's just because we can't cover everything. So, but you can sort of say hint where the difference in these angles can cause a beaming. Again, we're going to make the same answers as we did in the Componisation, right? That on average, though, cosine of theta is going to be 0, because we have as many in the fore-aft. It's fore-aft symmetric, and this is going to be 0. So you can say that here now, nu out, in this case, is nu out divided by nu is 0, gamma squared. But this, of course, is greater than 0, right? In the low relativistic limit, we don't get an effect. In the low velocity limit, we don't get an effect. Gamma is unity, right? And yeah, we don't have the frame effect of relativity, so we're back in the Thomson. But whenever we have a significant relativistic effect there, so that V is close to the speed of light, relatively close to the speed of light, you see that actually we get the other effect here. The photon energy, the outgoing photon energy is going to be higher than the incoming photon energy. That is that we have pumped the photon energy. So we're pumping the photon energy. We're making them more energetic, or we are producing a hardening in the spectra. Now, of course, that energy has to come from somewhere. We're still, we still have to preserve energy. So it comes at the expense again of the gas, but the opposite as what we saw in the Componisation, the gas cools. So the energy of the photon goes up, the temperature of the gas goes down. This is, of course, why it's called inverse Compton, because it's the inverse of the Componisation. And like I said, again, this is a minuscule effect, very, very small. However, the very interesting thing is that with modern techniques, it's observable. And there is one, as I alluded to in the beginning, very important application of this in astrophysics, and that has to do with the following situation, which we will now just schematically sketch out. We have our cosmic background radiation, okay? Cosmic background radiation streaming towards us here, right? And we know that this is cool. Today it's 3 Kelvin. Perhaps at this redshift it was a little bit higher, but not much. So it's going to be, say that's roughly in the local universe. So it's going to be around 3 Kelvin. Very low energetic photons in the microwaves, right? And now these photons that are on their way to us, they go through a gigantic galaxy cluster, which can be a cluster of galaxies containing on, I don't know, thousands of spirals, ellipticals, and whatnot. Okay? Now, in between these individual galaxies in the cluster, there is a medium which is extremely hot, the intergalactic medium. And that, as we will talk about during the spring, is extremely hot, many million kelvins. Okay? So as the photons go through here, they are subject to the inverse Compton effect, such as you get a hardening of the cosmic background radiation spectra. So if your undisturbed cosmic background radiation spectra looks something like this, I knew, yeah, something like this, a bad drawing. Then this will be shifted to dunk, like this. So at the high energy end, you will receive more photons. At the low energy end, you will receive less photons as compared to your aunt. And there will, of course, be some sort of transition point here as well. Like I said, this picture is highly exaggerated. This is a tiny, tiny, tiny effect. Now, galaxy clusters, on the other hand, they're huge. So this can happen many times. And the interesting thing is that this effect is observable. It is called the Sunayev, oh my God, Zeldovich effect. This is misspelled. Sorry about that. Sunayev-Zeldovich effect, okay? And it has turned out to be one of the most important observational tools that we have to map out the large scale of the universe. Because if you measure this shift, you can get information about the properties of the large-scale properties of galaxy clusters, and those are extremely important then to constrain how our models for structure formation in the universe behave. And remember the connections here. We have analyzed in quite some detail the cosmic background radiation, how it was let free. We did a little thing in the beginning like, well, actually there is some, it's around 3 Kelvin, but there is some delta T there, right? There is a delta T of on the order of 10 to the minus 5. And that reflected the perturbations at the time of release around the era of recombination. Now those small perturbations then, they grow to cause all the structures in the universe that we see today. Now, of course, they grow over time, right? So they weren't the same back then, you know, as they are today, obviously. And by putting this into often numerical models following this structure formation over time, then you can get some typical constraints. And by using the Sunayev-Zeldovich effect then, you can see how those predictions of the models compare to the actual observations that we see. So that's a qualitative explanation of this. We will discuss it, like I said, a little bit more during this break. All right, that was Compton scattering and inverse Compton scattering.